Esto con la chaqueta no se ve. Déjamelo cerca de la mano que pueda darle al mute si hace falta. Hola, hola. ¿Se escucha? Vale. A ver. Y así sí. Okay. Can you hear me? Yeah? Okay. Well, let's start with the presentation. Thank you very much, Fernando, Silvia, and David for being part of my panel, and everybody, and also Daniel and Julio for their supervision in my thesis. Let's start with this. The title, we already said it, so I'm going to jump into the contents. Okay, today we're going to see the motivation and objectives of the overall thesis. Then I'm going to explain a little bit of the experimental methodology, because I made an emphasis on the experimental methods and the things that I've been learning and developing during the thesis. Then we will see the results, the publications, and the motivation of all the papers that we published. And then I will develop three of the chapters of the discussion that I think are the most interesting here to discuss, and some conclusions, of course. Okay, so first of all, why do we do high pressure science? I think all of us here in this field know that we have a lot of applications and things to learn. So I just highlighted some of them because I think fundamental science is explained by itself. We want to know everything, and we want to explain how the world works. But in high pressure, we try to see, well, some phase diagrams, the physical properties of the materials when they are applied such conditions. But, well, this is something briefly. And then I want to motivate a little bit the vanadates. So these materials, if we pay attention to this figure of a paper of my director Daniel, it's relating the radius of both A, that will be the metal, there are some metals here, and this line will be associated to vanadates, that is the X. So we can see that most of them, that just this case of vanadates, the trivalent metal orthovanadates, are mostly packed in zircon type when they are at ambient conditions. But then I'm highlighting these phases because when you apply pressure, they switch and they change phases into those kinds. So we find typically zircon to scheelite type. I have a compound that goes from fergusonite to scheelite, and then they go to monazite. But, well, in brief, vanadates are rich in polymorphism, so they are really interesting in terms of properties, applications, and we are not only studying trivalent metal orthovanadates, we also have divalent metals, metavanadates, pyrovanadates, spinel ones, and a couple of examples of practical applications. There are some publications about these two orthovanadates being applied in nanostructures, or this one that we discovered that has one of its unit cell directions being really non-compressible. Which are the objectives of my thesis? Well, of course, I want to share with you all of the results and all the really interesting things that I've discovered. This is one of the figures that I'm most proud of it because it contains a lot of information just in 4 sections. We are going to discuss this later. And also, I took advantage of this thesis in order to transmit all the experimental experience that I've gathered. It's not only the results that are going to be reflected on my publications, but also all the information, all the experiences, all the techniques that all the people around me taught me and helped me to develop. So I want this to be reflected in my thesis. Well, so I cannot avoid talking about the diamond Alby cell. This is the heart of high pressure science. This is an image of it. It's rather small. So being able to apply hundreds of gigapascals nowadays with just something that is this big, it's amazing. It's just because the relation between pressure and the other magnitudes are force divided by surface, we don't need too much force. We just need to reduce as much as we can the surface in order to achieve higher pressures. And this will be a scheme, but I'm not going to tell much detail because you already know how this works. This will be a couple of examples of loadings. This is powder loading, and I'm going to criticize a little bit myself right now because I can say there's three main parts: the sample that I want to measure, the way I know the pressure inside, the pressure gauge, and the present emitting media, in this case neon gas. Well, this pressure gauge is contacting the gasket, so it can be contaminated. There's too much pressure gauge, a huge sphere of copper. Well, we can improve that. So in the end, I improved and I did some single crystal experiments. The single crystal is right in the middle, so it's the better positions to cover as much angle as we can to get into the reciprocal space. The ruby is pretty small, it's far away from the gasket, so I got better during the experimental exercise. These are the two types of pressure gauges that I use during the experiments. So as far as we can, we try to do the ruby method. So if we point the ruby with some laser, we excite the luminosity. We see this couple of peaks. This principal peak, R1, is the most characterized. So we use this in order to check the pressure inside. But sometimes in XRD experiments, if we are able to put some copper or gold inside the loading, as it is cubic, it is not going to react with the sample, and it's easy to find because it has fewer peaks. It can accelerate the process. But I think Ruby is more trustworthy for this case. Okay, so the XRD experiments were held in synchrotrons. All the powder ones were in Alba in Barcelona, and the single crystal ones were in the ESRF in France, Grenoble. And this will be a general scheme of synchrotron line. We have the source, the boosting ring of the electrons, then the main ring that is going to radiate X-rays because of the accelerating the electrons into close to the speed of light. Then we have an optical hatch. This optical hatch for an XRD is going to be an insertion. It will need an insertion device, and will tune the signal in order to be monochromatic with the correct shape. And then we have access to the experimental hatch when we locate the diamond anvil cell, restrict the signal with a pinhole, and we get in the detector the diffraction of the sample. Then we also have Raman results. Most of them were measured here in the university. In this case, we have either way two lasers that will have a power of 2 milliwatts, but this is too much, so with a rotating polarizing, we get it down in order not to burn the sample. We need some filters in order to have a good signal of just the laser. Then, in the Blin splitter, it goes into the sample and reflects the signal, and it's filtered in order to get the Raman signal. But also we can add a rotating polarizing that in team with this, we can do polarized Raman measurements. But well, this is more or less the setup that we use. After getting the information and the spectra, we have to analyze and process this information. So when we have powder XRD, we always have to integrate the diffracted image into a spectrum. So this is always done with diopters. And then we choose our software of preference. I used Powderther and Rex at the beginning, and then I discovered Profex. So I switched into that, and this is the one that I'm reflecting on the thesis, and is the one that I'm recommending. But it's up to the experimentalist to choose. Then, if we use single crystal ones, there is not just one diffraction image. We have a lot of them. In my case, 128. So I have to process all of them, in this case with Chrysalis, and recognize the most repeated reciprocal space, or the structure that is most fitting the most peaks, and reduce it in order to check that is the correct one. When we resolve the lattice parameters with Chrysalis, then we can feed this information to OLEX Orjana in order to find the atom positions. So this is different from the powder, because we can find atomic positions with Rietveld analysis with powder, but in high pressures the diamond Albi cell is going to condition this. So in this case, single crystal have a little advantage here. And for Raman spectroscopy, the free software that I've seen the most is FITIC, but in our case, we had access to MATLAB and some functions, for example, Julio gave me that are really useful, so I took advantage of this. And then when we try to find the pressure coefficient of the modes, we just use some fitting tool in order to get it. Okay, so we reach the results and publications. During my 5 years of research, I've published, and we've published, 7 papers, including 8 samples, because here the nickel and cobalt orthovanadies were really similar and related. And let's jump into all of them. So first one, bismuth orthovanadate. This one has a really interesting ferroelastic second order phase transition from Fergusonite to shellite type. If you remember at the beginning, I said that these materials are usually seen in the zircon structure at ambient condition, but in this case the natural structure is the Fergusonite type, and this is metastable. Okay, so we can get this at ambient conditions, but once we apply pressure or temperature, it goes to shellite and it's not reversible. The reversible one is the Fergusonite. And in this case also, we found at 16 gigapascal that it has another phase transition into a monoclinic structure, and I will explain later why the results are not that prolific for this structure. But well, we got to do 8 different experiments, so we try to relate all of them. I'm going to develop in the discussion sections more results of this, so this is just the motivation of each paper and the main results. Okay, so for erbium orthovanadate, in this case, we have some single crystal, and we also seen in the literature and our measurements that the phase transition from zircon to shellite was sluggish. It was really extended in pressure. They were coexistent too much, and we thought maybe there's a intermediate phase in here that we are not measuring. Let's try to do this experiment the best as we can with single crystal and with helium as pressure transmitting medium. And what we saw is direct phase transition, no coexistence, and also the shellite still being a single crystal. That is something that we got lucky because you have a volume collapse at this pressure. So they used to got you get polycrystals, or a signal that is not well for analyzing single crystal, but we got it, so we were really lucky. So for calcium orthovanadate, this is divalent metal, so it's a different family. We have a collaboration with Professor Paskovich in Warsaw, and this one has a special structure, this with locate type trigonal structure that is huge, and they did the temperature measurements, we did pressure measurements, and got to see a phase transition that is not seen with temperature. These were new. And we also got to update the pressure data that we had previously. For nickel and cobalt orthovanadates, they have the same structure, an orthorhombic one. And in this case, we focus more into the vibrational analysis because we have very large single crystals. So we had the opportunity to orientate them. And this allows us to do Raman, polarized Raman, and also polarized infrared measurements. So in this case, those samples up to 20 GPa do not change, do not go through a phase transition, but their vibrational characteristics are reflected. Now we go to the metavanadates. In this case, lead metavanadate. It has a special structure, so metavanadates usually packed in the bromurite type, a monoclinic structure in nature, but in this case, this metal is too large, so the structure is different. We analyzed it, and we got to see the evolution in pressure of the lattice parameters and also the Raman modes, most of them, even though it had 54 modes. And in this case, the B parameter is very short. It starts around 3.6 Armstrongs. And with pressure, we see that something weird is happening here, but we will explain it later. This one, the cobalt metavanadate, should be bromurite at nature, but we got columbite single crystals. This is a metastable phase. And we performed some Raman experiments without knowing what was going to happen. And we saw, XRD and Raman experiments, sorry. We saw that at 20 GPa, it goes through a isostructural phase transition. So it stays at the same structure, but the atom positions shift in a way that I'm going to explain later. And then at 44 GPa, we have another phase transition, this time to a monoclinic structure. We see here that even though the structure is the same, it has a noticeable volume collapse, and yet the last one is totally different. Last but not least, we have this espinel vanadate. It's a cubic material, and in this case, the sample has a lot of impurities, let's say, but they are not against the analysis. We will see that these impurities form part of the pressure mechanism that this material goes through. Okay, so now the main part, the discussion. These are the 4 chapters of discussion in the thesis. These are the 3 that I'm going to develop. And the last one I'm just going to mention that it is important for us in high pressure to get to the main result. The main result will be for us the isothermal compressibility of the lattice parameters and the bulk moduli. That is going to tell us how compressible the material is. In the case of the orthovanadates, we already had some studies about this, so they were similar to the expected ones, and the columbite type metavanadate was new, so not really comparable with anything else. For these ones, they have special structures, the cubic one and the Whitlockite huge one, and they show very little bulk moduli related to structures like this, just to mention. And finally, the lead metavanadate has this isothermal compressibility axis. The B1 is near 0, so for industrial applications in coating and things like that will be interesting to investigate that. And for nickel and cobalt orthovanadates, we saw that they have the same is isothermal compressibility for all axes except the B1. And in the B1, they are mainly located the nickel or the cobalt metal. So in the axis that we have this metal, if we change it, we see that the nickel orthovanadate acts like a compressed version of the cobalt one. And this is afterward affected with the pressure events, like the evolution of the modes. We see that they evolve the same or they cross similar, but later in pressure because of this relation. So let's jump into the phase transitions and pressure transmitting media. I'm relating these two things because sometimes they are really one affecting the other. Of course, the pressure transmitting media sometimes affect the phase transitions. And also, I'm going to leave here the material that I'm talking about because as I am covering a lot of different vanadates, I don't want you to get lost, but I'll try to do it not too fast in order to follow me. Okay, so for lead metavanadate, we had its own structure, different from the typical Brannerite type for the metavanadates. In this case, we saw with pressure, this is for the three pressure transmitting media that we used, neon, methanol, ethanol, and silicon oil. These two peaks, when using liquid pressure transmitting media, it went to the left. So what does it mean? When you are doing high pressure experiments, you expect the diffraction peaks go to the right, because this means that the structure or the lattice parameters are shrinking, are collapsing due to the pressure. But in this case, they did something that was not expected. So we said, okay, we have to investigate if this is something not expected, a phase transition, or what's going on here. So in this case, the animation is not working, but well. When neon was used for this 0.11 Miller index peak, it went to the right as expected and saturates here. When we used methanol ethanol, that is not as hydrostatic in this pressure range, it went a little bit to the left. And then when using silicon oil, that is even less hydrostatic, it jumps to the left. Why is happening this? The B-axis is the shortest one, and when reaching the pressure, the hydrostatic limits of each pressure transmitting media, the conditions inside are no longer hydrostatic. So here with the volume, we see that perfectly silicon oil, when it reaches the limit of around 3 gigapascals, it doesn't behave as expected. For the methanol ethanol, at around 9 GPa, happens the same. And neon follows the line of the calculations. So in this case, the C and A axis or phases are getting the most pressure, and as not being hydrostatic, the B axis has to expand in order to conserve the equilibrium there. So this is not a phase transition, it's an effect of the pressure transmitting medium that we see because we had 3 different experiments. Now we are changing material. We are in calcium orthovanadate, and we can see closely this 3,800 Armstrong cubic of a unit cell. That is really big. When we are dealing with other materials, it's around 100 of Armstrong cubic, so this is huge. We have also partial positions for calcium, and yeah, this is really difficult to understand by the bare eye, but you can study it and see how it works. In this case, we indeed had a phase transition at around 10 GPa to a monoclinic distortion of this group. But we suspect that this phase transition, that of course happens because we have some extra peaks from one pressure to a higher one, it's because of the pressure transmitting media, the medium in this case. We are using methanol, so the pressure limit was around 10 GPa, exactly the pressure of transition of this material, and the calculation said that it should be at the same structure. So we suspect that this is driven because of the pressure transmitting media. Okay, now we go to the bismuth orthovanadate. This one, we studied this ferroelastic second order phase transition and also the metastable zircon to the scheelite phase transition, both in pressure and temperature. Okay, this is also pressure and temperature. In this case, with pressure, we see these two axes merging into one. So Fergusonite and scheelite are related in structure. This monoclinic structure is losing the angle and going into 90 degrees, and these two axes are merging into one, as we see here. And we can also see this with temperature. Both axes merge into one afterwards. In the case of the zircon scheelite phase transition, it happens at around 6 GPa. It's non-reversible, so if we go back, we still have scheelite, and at the end, we saw Fergusonite. So the natural one indeed is the Fergusonite structure. We merged 4 experiments in order to build this phase diagram. In this case, a couple of pressure experiments, 1 temperature experiment, and an extra one combining both high pressure and high temperature. So in this case, we go up in pressure, then we stop, go up in temperature, stop, pressure, temperature, okay? And we go back and forth in the phase transition. In this case, we can clearly see that this phase transition has no hysteresis. The second order behavior related to it in a way that it has no hysteresis. And this is the result that was also published in other papers, so it is compatible with it. Just to mention this last phase transition, in this case, at around 16 GPa, we had the scheelite, and then a lot of extra peaks were adding to the scheelite ones. And we do the best to fit this. In this case, it was relating this structure with other materials in order to see which structure would be the best. There's also some other works in bismuth vanadate that proposed other phase transitions that are different from this one, but this is the best that we got. So I think that the best would be to get access to single crystal in order to get to this pressure and try to see this structure with better resolution in order to confirm which structure we are seeing here. Okay, for erbium orthovanadate, the lucky one, we confirm that this phase transition has no structure in between, and we saw single crystal behavior of the scheelite state. In this case, we see that the dots are a bit distorted and bigger, but this square-like signal of the same cut in the reciprocal space have different shaping. But you can ask me, okay, it's different, but are you sure that it is scheelite? Can you confirm it? Well, we can. If we go to selection rules of each structure, the only rule that is different is the one highlighted here, okay? And if we go to a cut in the reciprocal space that has this relation, like the two first ones are the same and the last one is different, this reflection is the -1, -1, 4. Okay? So, if it is shellite, it should be the last one, even. Yeah, 4 is even. But if it is zircon, if it is still zircon, it is not a phase transition, 2 times H, that will be -2 plus L, 4, 2 equal to a multiplier of 4 is not true. So we confirm that this is shellite and the phase transition is direct. Okay, this is cobalt metavanadate in the columbite structure, this one. This is right before the phase transition and right after. Just 1 gigapascal of difference here. And we can see with the bare eye already the changes. Like the oxygens, that you can see the ones behind have green and pink, orange, green. Here they are all allineated, so you can see them. And also we have this titanium oxide that has the same structure here, the columbite one, and also suffers the same afterward phase transition. I'm marking it here in order to check that they are the same. This is really similar to this section. Okay. So getting into the detail, these are the bond distances between the cobalt and the oxygens. Okay, we have 3 different ones. The average one is the one empty, and the lines are calculations. Okay, so we see that they are in agreement. And for the cobalt octahedra, it shrinks after the phase transition. It jumps. All the bonds got shortened. In the case of the vanadium, we have 6 different bonds, 3 larger than the average and 3 shorter. In this case, the average stays the same, but the shorter one got larger and the largest got shorter. So it symmetrizes. The octahedra is more symmetrical for the vanadium case. So this is seen with the volume of each polyhedron. The cobalt one shrinks, and the vanadium one stays the same in volume, even goes a bit higher, but symmetrizes. The distortion index tells us that this octahedron is symmetrizing. And also you expect a 6 coordination in an octahedron. This is always true for the cobalt, but with the vanadium it gets closer with the pressure. And then the last phase transition was also resolved with single crystal methods, and it gets another oxygen into the octahedra, so now it's 7-fold coordinated. We also see these transitions in Raman. In this case, we start with the columbite with some extra peaks that I'm going to discuss in the impurity section. And when going to 20 GPa, the modes are the same but jump into the right. So this volume collapse but still being the same structure permit that this goes here, this goes here, this goes here. So it's the same but into the right. But if we check the next phase transition, all the modes are different. So this is another structure here. And Raman also add that if we go back in pressure for the XRD, we lost the loading, so we couldn't do the compression. We saw back the structure, so both phase transitions are reversible. This is the last structure. This is a monoclinic new structure for cobalt vanadate, and this phase transition was also seen for titanium oxide. So in this case, they synthesized it directly at 32 GPa and 800-900 Kelvin in order to get this sample. We got it just with pressure, but the columbite baddeleyite phase transition was also seen for us. This is all for all the phase transitions that we see during the experiments. Now we are going to discuss the impurities in the sample. That is something that experimentalists cannot avoid. For lead vanadate, metavanadate again, we had some vanadium oxide and lead oxide in the sample that we had to consider, but we got lucky, and as the pressure increased, these impurities, the contribution was very little, so we could ignore them and just focus on the main sample. So this is one case for impurities. Another case is the cobalt metavanadate in the columbite structure. So these extra Raman contributions were from the brannerite type, the natural structure. And why we didn't realize that we have brannerite type until we did the Raman, because we did the XRD previously. Because when you are doing single crystal measurements, you just focus on the main sample, the main signal that it's getting in the reciprocal space. So this was just rejected. But as we went back in pressure, when we opened the diamond albite cell and performed the Raman, we perfectly see the brannerite signal. This is not reported, so if we compare it with zinc metavanadate and magnesium metavanadate in the brannerite structure, the profile is exactly the same. But not all the sample went back to brannerite. We had other places where the sample had a different signal. We did this with a single crystal, so it got polycrystals inside. So we don't know exactly how the mechanism of reverting works, but at least we got the brannerite signal. And now the spinel iron vanadate. In this case, we saw from an XRD at the ambient pressure that we had extra contributions from other compounds that were not related to this expected one. So we had to add some proofs in order to identify them. One of them was the EDXS, that is telling us which elements and in which ratio are found in the sample. So it's just oxygen, vanadium, and iron in this stoichiometric relation. So it has to follow this rule. And also with the Raman, we identified some modes compatible with vanadium oxide, plenty of them, and this one just related to iron oxide. So we know these three are playing here, and in order to have the best Rydberg fit, we had to add also an orthorhombic phase of this iron vanadate in order to get this best fit, and the proportions of the materials. The main sample is still spinel iron vanadate, then we have the oxides, and this last one that has an interesting cut of the amount. Then, when we add pressure, we saw that the amounts of the oxides went increasing from 12 GPa. Up to 12, it's still the same amount for everything, and then the reflections related to these oxides went up, and the main one went down, and this one stayed the same. So the main sample decomposes into iron oxide and vanadium oxide in a way that it stays the same with the proportions, and at the highest pressure, this is the difference. But on top of that, when we go back in pressure, this decomposition also reverts, and these oxides recombine to get back into the main signal of the sample. This is all for the impurities, and then we will check how to identify the symmetry of the Raman modes, because in this case it adds plenty of information for the discussion of the vibrational properties. I'm going to start with the best case scenario, that is the case of nickel and cobalt orthovanadates. When you have access to single crystals big enough to orientate them, you can do polarized Raman in order to split the contributions with the symmetry. So if we apply group theory, and in this case I checked the Bilbao crystallographic server in order to get those matrices, the tensors, well, it says that if we polarize the inciding light and the reflected light with the same orientation, we get A modes. And if we cross the polarizing of the light, we see the B ones. So for example, this one, the beam is in the Y phase of the sample and is reflecting on it. That's what it means. And this says that the inciding light is polarized in the Z direction, and the reflecting one in X. So the inciding in Z and the reflecting in X is this matrix. It is B2? Yeah, it is B2. So we got access to phases, to the Y phase and to the Z phase. So we got to see the cross of the other ones, the B1 and the B2. And we got an extra cut of the sample that was not a main direction of the sample, but we knew how much we had to rotate the diamond anvil cell in order to get to that phase. So we started in the Z phase and we rotated 33 degrees. So this phase, called it in a different letter, has contributions of both B1 and B3. And as we already know, B1, we can get the B3 contributions. This is a different case. This is not the ideal one, but it's something that also works in order to relate the symmetry with the modes. This case, we have for lead metavanadate 54 modes. There's a lot. And me being an experimentalist, putting 1, 2, 3 contributions inside here, I think is bold. Like, why are you doing this? How can you demonstrate this? Well, I have 2 extra information in order to do this. The first one is the pressure evolution of the modes. So as the pressure increases, some of the modes split and merge. If we check here, we have this black one that gets into the other ones. And sometimes you have one that is traveling all along. So the vibrations are affected by the pressure differently. So I can split them. And also, I have the calculations. And calculations also told me how many modes I have there, and also double check me the pressure evolution. This crossing is different. Well, but I expected it. Or this one here also happens. So I have 2 extra information that allows me to differentiate all 54 modes. And this will be the reality, and it's a pity because we had single crystals, but they were too little in order to orientate them. So we just did the Raman, and we didn't have as much contributions as more calculated modes. So we couldn't say the symmetry of each of them. Well, I can tell this one because it's the one that is softening and happens the same with the calculation and tells me a phase transition is going to happen. Well, but not the rest. So it was just tentative in this case. So this is the end of the discussion. We reached the conclusions. 45 minutes, so good time. Going to stop a bit. I'm going to highlight one conclusion for each sample or for each work. Okay, so for the bismuth vanadate, we saw the second order ferroelastic phase transition in pressure, temperature, and combining both of them, and confirm that it has no hysteresis in this range. For the erbium vanadate, we confirm that there is no intermediate phase in between this phase transition, and indeed is direct. If you apply the ideal pressure conditions, you get the phase transition directly. For the calcium, we got a phase transition in pressure, but we had some clues in order to assign it to an effect of the pressure transmitting medium. If we compare nickel and cobalt orthovanadates that have exactly the same structure, we see that the nickel one acts like a compressed version of the cobalt one. For the lead metavanadate, we saw that the B-axis is highly incompressible, it's sensitive to the pressure transmitting media, and has promising practical uses that should be investigated. For the metastable columbite cobalt metavanadate, we discovered 2 new phase transitions, one isostructural, with the very useful information of the single crystal signal, and another one to a monoclinic structure. And finally, the spinel iron vanadate has impurities in the sample, but in the end were part of the pressure mechanism of the sample. So this is everything. Thank you, everybody, for being here, and that's all.
Thank you very much for your clear presentation. Now take a break before starting the next session.
Okay, whenever you want.
Are you ready for that?
Yeah, of course.
So we start the questions and comment session, and we start Dr. Silvia Cata. So
Thank you.
So first of all, I would like to congratulate you on your work, you and your PhD advisors, and you can hear me.
Do you want the mic?
For me, it's fine. For you,
Yeah, I hear you. Yeah, I can turn off mine in order not.